Hello everyone, our group is Group 38 and our project is Quantum Optimization for Ancestral Recombination Graphs. I'm Alexandria Allen and I'll be presenting alongside my teammates Brandon, Ellen, Diego, and Amira. Our project intersects quantum computing and computational genomics, and today we'll walk you through our goals, design, implementation, and results. So let's get started. Our primary objective was to develop a QAOA pipeline to construct minimal ancestral recombination graphs, or ARGs. The core idea is to use quantum optimization to find the ARG configuration with the fewest recombination events. To make that possible, we reformulated the problem as a QUBO, an Ising model, allowing a quantum circuit to explore many candidate solutions simultaneously. The project was divided into 5 subsystems. I handled input validation and synthetic matrix formatting. Brandon built the QUBO model with its constraints and Hamiltonians. Ellen designed the QAOA circuit and p-layer optimization. Namira handled output, extraction, visualization, and performance evaluation. And Diego managed real genomic data preprocessing and integration into the pipeline. On the requirement side, our functional requirements specify that the system must accept a binary S&P matrix as input and output a minimal haplotype assignment. Input data must be validated and cleaned before reaching the QUBO formulation. The QA circuit must support adjustable depth via p-layers and log energy per iteration. Results are automatically exported as PNG and CSV files. For usability, our subsystems communicate through standardized NumPy matrix interfaces, which keeps integration clean and consistent across the pipeline. Configuration logs are maintained throughout processing to ensure every run is as repeatable and traceable. The entire code base is structured as importable Python modules, which makes it maintainable and easy to extend as the project scales. For safety and privacy, we ensured no identifying personal data would be used if sourcing from the public 1000 Genomes project. Our preprocessing step removes or flags any invalid or missing values before data enters the pipeline. It's worth noting that real genomic data integration was not completed this semester, so while these requirements were researched and documented, they weren't exercised with live data in practice.
On the technical side, we face significant hardware and algorithmic limits. So the current quantum simulation is resource heavy. The qubit counts and circuit complexity scale exponentially with problem size. On the Athena HPC, we are currently capped at roughly 5 by 7 matrices. And beyond hardware, there's a penalty balance. So if our QUBO weights are imbalanced, the Hamiltonian becomes poorly defined, leading the solver away from the true biological solution. Our scope was also bounded by these data requirements. The algorithm specifically requires phase haplotypes, so any unformatted or unphased data causes immediate runtime errors. While we established a pipeline for real 1000 genomes VCF data, the preprocessing required to fit these into a clean matrix format meant that our primary execution remained focused on synthetic sets to ensure mathematical accuracy within our semester timeframe. To manage these constraints, we adopted a start small philosophy. We began with 5 by 5s and 6 by 6 synthetic matrices to verify our logic before attempting larger runs on the cluster. We also built an input validation layer as a defense measure. This catches formatting issues before they reach the quantum circuit, which saved us hours of debugging time on the HPC. Our architecture follows a hybrid loop structure. So it begins classically with data modeling and QUBO construction. We then map those variables into an Ising Hamiltonian for the quantum circuit. The QAOA layers explore the probability space, and the resulting measurements are passed back to a classical processor. If these objectives aren't met, the classical optimizer adjusts the parameters and restarts the circuit. This is a cycle that continues until we reach the most parsimonious solution. This block diagram highlights the specific handoffs between software modules. It starts by putting all possible solutions into a superposition, meaning it can explore many possibilities at once. Then it applies 2 key operations repeatedly. The cost Hamiltonian penalizes bad solutions like the one with too many recombinations. The mixer Hamiltonian helps explore different neighboring solutions. After that, the system is measured, which gives us a probability distribution over possible solutions. A classical optimizer then evaluates those results and updates parameters to improve the next iteration, and this loop repeats until the solution stabilizes, meaning we found a strong candidate for the optimal configuration. Finally, we manage the state flow between team members using standardized NumPy interfaces. A key innovation was the prepare validated matrix helper function. This single call wraps Alexandra's validation logic and Brendan's Cubo builder into one reusable step. This common interface ensured that no matter who was running the notebook, the data flow remained consistent and error-free across all 5 subsystems.
Here are some of the main design decisions we made during implementation. We added a helper function called prepare validated matrix to act as a clean integration layer between subsystems. We also made sure validation happens before building the Cubo, so invalid data never reaches the quantum part of the pipeline. Finally, all results like CSVs and PNGs are automatically saved for each run, which helps with reproducibility and comparing experiments. This slide shows how the problem is modeled. We first encode the ARG problem as a Cubo, where penalties are added for incompatible SMP pairs based on the 4-gamete test. The cost function combines breakpoint counts with penalty terms. Then we convert that Cubo into an icing model using a variable substitution, and that Hamiltonian is directly encoded into the quantum circuit using Qiskit. For execution, we use QAOA with a configurable number of layers, where each layer applies cost and mixer operations. We use a classical optimizer, COBYLA, to tune the circuit parameters, and the output bit string is decoded into recombination breakpoints. For real data, we built a pre-processing pipeline that converts phase genomic data into the same binary format used by the QAOA system, so it can integrate with the existing pipeline. This slide covers the input validation subsystem. It checks things like matrix shape, data type, binary values, and uniqueness before anything goes into Cubo construction. We also wrapped everything into a single function so validation and Cubo generation happen together. During integration, we ran into a bug with NumPy iteration, which we fixed by casting values to integers before comparison. Finally, we deployed the pipeline on the FAU HPC cluster using Slurm job scripts. Jobs were submitted through on-demand, and we tested the full pipeline on smaller synthetic matrices like 5x5 and 6x6. This helped us verify that everything runs end-to-end in a higher performance environment.
So for project testing, we did 3 types of testing. The first was unit testing, where we tested each piece of the pipeline individually on its own. So things like matrix formatting, missing value handling, circuit construction, and as well as the Cubo shape output were each tested on their own. And then it was integration testing, which is where we ran the full pipeline end to end on smaller synthetic data sets of matrices of size 5x5, 6x6, and others. And we verified the flow, so from input to Cubo to icing to QAOA, for it then to decode and then visualize it. And next was the performance and scalability testing, where we used the HPC cluster to log runtime and memory and tested the QAOA at different depths of like 1 to 4 to evaluate trade-off between convergence speed and accuracy. So for the actual testing results, we will start with energy convergence. In energy convergence, all 4 of the circuit depths start scattered in the first 10 or so iterations, and then they begin to stabilize around -14 to -15 energy. This tells us that the classical optimizer is actively adjusting the quantum parameters and pulling them towards a lower energy solution, which is exactly what we want to see for this experiment. And then for the accuracy against the baseline, we tested QAOA at 4x6 and 5x7 problem sizes against exact brute force and greedy heuristic methods. And it was shown that the lines overlap, which means QAOA is matching the optimal solution at both sizes. And this will be shown in the next slide. So this is the chart showing the comparison of exact brute force, greedy heuristic, and QAOA at depths P2 and P4 visually. On the x-axis is the two problem sizes of 4x6 and 5x7, and on the y-axis is the average objective value. So what the line shows is that all four of the methods are landing on the same values. Because like the lines are on top of each other, that confirms that QAOA is keeping up with the classical methods of exact brute force and a greedy heuristic as the problem scales up. So the next result we'll look at is the generalization and missing data experiments. For the generalization experiment, we trained the parameters on one base instance, and then it was transferred to new test instances and samples without retraining. And what was found was that it reproduced similar breakpoint counts across the samples. So that means that the performance was able to remain stable even without retraining, just by simply transferring it, which is a really good sign. That means it is not necessary to retrain every time a new sample is used. And then for missing data, the performance as well remains stable even with the missing data rate increasing. Of course, when it was really, really high, there would be some degradation, but otherwise the breakpoint objective did not have a significant degradation as the missing rates increased. So that means that the pipeline is able to hold up even when the data is incomplete, which is very important for ARGs, especially working with genetic data. So in this slide is the chart for the generalization experiment that was discussed in the previous slide. The blue bars are the retrained QAOA, and the orange bars are the transferred QAOA. So lower is better since we're looking at breakpoint count. On sample 1, both are 1, so they matched. And on sample 2, retrained jumps to 2 while transfer stays at 1, so the transfer actually did better. On sample 3, both are back to 1, so in all 3 samples shown here, transferred parameters either matched or outperformed retraining from scratch. So this chart shows the missing data experiment, which was discussed a few slides ago. On the x-axis is the missing data rate, which goes from 0 to 40%, and on the y-axis is the average breakpoint count, and for that, lower is better. So what you could see in the graph is QAOA in green actually starts higher than greedy, which greedy is in blue, but as the missing data rate increases, both come down and slowly converge towards 0. Greedy starts slower, but it also decreases like the QAOA. The point is that all the methods are trending downward, so QAOA is able to still work with missing data, and rather than just breaking down as the data gets more incomplete, which, as I previously mentioned, this is very important when working with genetic data.
Hello, my name is Brandon, and I'll be going over the rest of the slides. What was achieved? For this project, we were able to successfully build a full QAOA pipeline for constructing minimal ancestral recombination graphs. That includes everything from generating synthetic data, validating inputs, building the QBO and mapping it to an icing model, and then running the QAOA circuit to produce results. We also implemented full visualization and automatic CSV and PNG output, which made it easier to analyze results across experiments. On top of that, we got the pipeline running on the HPC cluster, which allowed us to test performance beyond local limits. We also explored parameter tuning and scalability and began integrating real genetic data through a pre-processing pipeline. In terms of our original goals, we were able to fully meet most of the core objectives. The main quantum optimization pipeline was successfully implemented and tested end-to-end. Our synthetic data validation system worked as expected, ensuring clean inputs before entering the quantum stage. Visualization and performance evaluation were also fully completed, giving us clear insight into how the model behaves. The only area that was partially completed was the real data integration. While we built the pre-processing pipeline, we didn't fully run real genomic data through the entire system within the semester's timeframe. One of the biggest technical lessons we learned was how sensitive the QUBO formulation is. Small changes in penalty weights can significantly affect the resulting Hamiltonian and overall solution quality. We also ran into issues with NumPy data types where certain values weren't hashable and caused bugs during validation. From a modeling perspective, we saw that increasing QAOA depth doesn't always improve results. After a certain point, the benefits start to level off. On the processing side, breaking the project into smaller stages and integrating step by step made debugging much easier compared to trying to run everything at once. We also learned that running jobs on HPC requires careful resource management, especially with memory limits. From a teamwork perspective, one of the biggest takeaways was the importance of clearly defining how each subsystem communicates early on. At first, mismatches in expected data formats caused some integration issues, but this improved a lot once we standardized things with shared functions like the validation wrapper. If we were to do this again, we would define those interface contracts up front before starting development. We would also begin scalability testing on the HPC cluster earlier so we could identify performance limitations sooner. And finally, we would allocate more dedicated time for real data integration instead of leaving it toward the end of the project. Hello everyone, my name is Brandon and I will be conducting the live demonstration of our quantum optimization project. Here we find ourselves in the main execution at the very bottom of our program file. I know in the previous slides my other team members have already discussed the different experiments that we run for this program to test the different, or to evaluate the different metrics between classical methods and our QAOA, as well as generating an ARG structure. What's good about our main execution here is it allows for command line arguments to be passed when running our file to give the user specifically what they're looking for. So as you see here at the very beginning of our main execution, we have our plotting functions that can be passed when calling the program file. For instance, you can plot the scaling from a CSV file, which is one of our experiments, or the missing data, generalization, energy convergence, and the three different graphs that come from our ARG structure experiment. Now we would only call these specifically if we were already contained the CSV files, but for now we will just be going through actually running our experiments. So as you see here, we have our experiments. We can run the scaling experiment with -- scaling, and this continues all the way down through the rest of our experiments. Or we can also run the -- all, and that's what we'll be doing today for our live demonstration to show how this can be ran with command line arguments. And here you can notice that I have already shrank the problem sizes and our number of trials just because it can become computationally expensive to do this. So let's go ahead and go into our Anaconda prompt to be able to do this and activate our quantum ENV, if I can type. All right, we're in our quantum environment, so I'll go ahead and run the file. With our -- all command line argument. Here you can see our scaling experiment running for 2 trials. And we were able to generate our graph as you saw previously. Now moving on to our missing data experiment. We are testing the 10% and 20%, as you can see right here, and everything operated correctly here. Everything overlapped, so we can see that this worked properly. Now we're on to generalization. It's okay to see 0 here because it's just counting the breakpoint counts. Now, so noticing that both samples are both at 0, this is really good because they overlap correctly. Here's our energy convergence experiment. And finally, we should get 3 graphs here for our ARG structure. Which is exactly what we got. And this is exactly how we would pass it into our scripts for the FAU's HPC to test bigger problem sizes. And that concludes our live demonstration. Thank you very much.